The final topic in multi-dimensional integration is how we handle variable limits of integration. For example, how do we integrate over a domain that isn't rectangular and whose boundaries might be given by some function? This is something that happens quite frequently. So for example, consider the upper semicircle given by the equation x squared plus y squared equals a squared. If we want to calculate an integral over this domain, we can't just use simple bounds. So for a given value of x, let's call it xi, the limits of integration are y goes from 0 down here to a squared minus x squared to the 1/2 up here. But for each xi, the limits of integration are different. So if we go to this point here, we can see that the limits of integration are going to be different. So it's not possible, for example, to use constant spacing between the points when we integrate this in the y direction. So for the integrals, there are a number of different things we could do. For example, we could use the same number of points for each y integral, but each y integral would have a different spacing, and that's represented in that figure there. Or we could have a different number of points for each y integral. If we were to do this, it also generally means that we're going to have different spacing on each of these integrals as well. Or perhaps we could use Gaussian quadrature for each y integral. We could use the same number of points for each integral or a different number of points, and it just depends on what we know about the function as to which method we would do. It doesn't matter, however, how the integrals are calculated. We're still going to do the same thing. We're going to choose a set of points, in this case in xi, and perform these integrals in y. So take that first point, the integral is going to be 0 because that distance is 0. Take the next point, do an integral in y, the next point do an integral in y, and go on and so on until we've done all of the different values of x and we have an integral of y at each of them. So we end up now with a set of values. Because we're actually integrating in y this time first and x second, what we have is we have an integral for each different value of x, and we're going to call that function g of x. So that's the integral in the y direction for each different value of x. And those are represented, so that integral there is represented by that point, that integral there by that point, that integral there by that point, etc. But this set of red points here now represents a function of x. And this function must be integrated with respect to x. In this case, it is our outer integral. Note the values at which the inner integral must be calculated are the xi, and we choose those xi depending on what kind of technique we want to use to integrate in the x direction. So if it was Gaussian quadrature, the x values would have to be Gaussian quadrature points. If it was Simpson's rule, they would have to be evenly spaced and there would have to be an even number of segments. So just a general comment on multidimensional integration. As a general rule, multidimensional integration is expensive. And because it's expensive, Gaussian quadrature, if it's possible, is the most efficient technique because it requires the least function evaluations. It's often better to split a domain into several subdomains, and that ensures that important features are captured and it doesn't waste effort where nothing is happening. So if we were trying to integrate this function that's represented by the contour in the figure here, we might split this up into, say, 9 domains. And in the inside domain here, we would use a high-order Gaussian quadrature to make sure that we pick up all of the variation, but in the regions or the zones outside, we could use a low-order Gaussian quadrature. Now, it's not always possible to know where to use what kind of integration before you start doing it, so there are some tricks, obviously, in trying to split up your domain into sensible subdomains. Bottom line is, for efficiency, even the most accurate techniques rely on taking as few function evaluations as possible, and that's why Gaussian quadrature is the best way of approaching multidimensional integrals, if you can do it. So in summary, the key points from multidimensional integration are, first of all, it's possible with Monte Carlo techniques, but they're not usually recommended. You can also do it by extending the one-dimensional techniques, and that's what I certainly recommend you do. When using 1D techniques, an inner direction must be chosen, or if it's a multi-dimensional case, you might have several inner directions, and then you calculate multiple integrals in this inner direction. Once you have done that, you then have a single outer integration to be done, which completes the process. Finally, variable limits of integration require a more bespoke methodology, and it's a bit hard to figure out exactly how to do this beforehand. You really need to look at things on a case-by-case basis.